Have you ever looked up at the night sky and wondered, why? Why are we all here? What's out there? And how does it all work? Well, you're certainly not alone. Hello, everyone, and welcome to The Big Why. I'm just as curious as you are about the universe and everything in it. From the depths of the ocean to the furthest reaches of space, no question is too big, no topic too strange for us. We'll crack open the mysteries of black holes, journey to the edge of the universe, and explore the mind-blowing discoveries that are changing our world. So if you're ready to unleash your inner scientist, ask the tough questions, and explore the universe alongside me, then buckle up, and let's ask why. We experience the world in motion, the Earth rotating on its axis, planets orbiting the sun, galaxies swirling through the cosmos. But what does it mean for something to rotate? Is rotation simply a matter of relative motion? Or is there a more fundamental absolute aspect to it? These questions lie at the heart of the concept of absolute rotation, a topic that has fascinated and puzzled physicists and philosophers for centuries. In this video, we'll delve into the complexities of absolute rotation, exploring its historical roots, its implications for our understanding of the universe, and the ongoing debates surrounding its existence. We'll examine the perspectives of influential thinkers like Isaac Newton and Ernst Mach, who held contrasting views on the nature of rotation, and we'll consider the experimental evidence that has shed light on this intriguing phenomenon. Whether you're a physicist enthusiast, a curious skeptic, or simply someone intrigued by the mysteries of the universe, this exploration promises to challenge your assumptions and spark a deeper appreciation for the fundamental forces that shape our world. And who knows? Perhaps by contemplating the nature of rotation, you'll gain a new perspective on the movement of celestial bodies, the behavior of subatomic particles, and the very fabric of reality itself. The concept of absolute rotation, the idea that rotation can occur independently of any external reference point, has been a subject of ongoing discussion and debate in physics. For this concept to hold scientific merit, it must be measurable. An observer should be able to differentiate between a rotation of an external object and their own rotation. Isaac Newton proposed two experiments to address this issue, one being the rotating bucket experiment. In this experiment, a bucket filled with water is suspended by a rope and set into rotation. As the bucket spins, the water initially remains flat. However, as the water gradually begins to rotate with the bucket, its surface curves into a concave shape due to centrifugal force. This curvature of the water's surface, independent of any external reference point, suggests the existence of absolute rotation. And number two being two spheres tied by a rope. In this experiment, two spheres are connected by a rope and set into rotation around their common center of mass. The tension in the rope increases as the spheres spin faster, indicating the presence of centrifugal force. This tension, again independent of any external reference, supports the notion of absolute rotation. These experiments, while simple in concept, have profound implications for our understanding of motion and the nature of space. They suggest that rotation is not merely a relative phenomenon, but can be an absolute property of an object or system. However, as we'll explore further, these experiments and the concept of absolute rotation have been subject to various interpretations and critiques, particularly in the context of Einstein's theories of relativity. In classical mechanics, Newton's bucket argument is often cited as evidence for the existence of absolute rotation. The argument hinges on the observation that the shape of the water's surface in a rotating bucket reveals whether the bucket, and by extension the observer, is rotating. When the bucket is at rest, the water's surface is flat. However, when the bucket is set into rotation, the water's surface becomes concave due to centrifugal force. This force pushes the water outwards towards the sides of the bucket, causing it to pile up and form a curved surface. Newton argued that if an observer sees a concave water surface but does not perceive themselves as rotating, then they must be rotating along with the water. This is because centrifugal force is only needed to explain the concave shape of the water in a co-rotating frame of reference, where the water appears stationary. In essence, Newton's argument suggests that the shape of the water's surface acts as a detector of absolute rotation, independent of any external reference point. However, this interpretation has been challenged by other thinkers who argue that only relative rotation is meaningful. Bishop Berkeley and Ernst Mach, for example, proposed that the rotation of the fixed stars relative to an object is equivalent to the rotation of the object relative to the fixed stars. They suggest that the centrifugal force experienced in the rotating bucket is not due to absolute rotation, but rather to the relative rotation between the water and the distant stars. While Newton's arguments may not definitively settle the debate, they do establish centrifugal force as an operational definition of absolute rotation. The presence of centrifugal force, as evidenced by the curved surface of the water, indicates that rotation is occurring, regardless of whether it's relative to absolute space or to the distant stars. This ongoing debate highlights the complexity of the concept of rotation and its relationship to the broader framework of physics. While Newton's argument provided a compelling case for absolute rotation with classical mechanics, the advent of Einstein's theories of relativity would challenge and refine our understanding of this phenomenon, leading to a more nuanced and complex picture of motion and the nature of space. Newton's second experiment, involving two spheres tied by a rope and rotating about their center of mass, offers another perspective on absolute rotation. In this experiment, the tension in the rope serves as an indicator of rotation. If the tension is non-zero, the spheres are rotating, regardless of whether the observer perceives it or not. This experiment is similar in principle than the rotating bucket experiment because it doesn't rely on gravity. The tension in the rope arises solely from the rotation of the spheres and the resulting centrifugal force. But beyond simply detecting rotation, this experiment allows us to quantify it. By measuring the sphere's rotation rate and comparing the calculated tension to the actual measured tension, we can determine whether we are in a stationary or rotating frame of reference. If the calculated and measured tensions agree, the observer is not rotating. However, if there's a discrepancy, it indicates the observer is rotating, and the magnitude of the discrepancy reveals the speed of rotation. For example, if the calculated tension is higher than the measured tension, the observer is rotating in the opposite direction of the spheres, and the greater the difference, the faster the rotation. The tension in the wire represents the centripetal force required to maintain the rotation. A rotating observer experiences both the centripetal force and the physical effects of their own inertia, which manifests as reactive centrifugal force. Whether these inertial effects are attributed to a fictitious centrifugal force is a matter of interception and choice of reference frame. In essence, Newton's two spheres experiment offers a more direct and quantitative way to measure absolute rotation compared to the bucket experiment. The tension in the rope serves as a clear indicator of rotation, providing a measurable quantity that can be used to determine the observer's rotational state. The debate over absolute rotation took an interesting turn with the introduction of special relativity. In 1913, French physicist Georges Sagnac conducted an experiment similar to the Michelson-Morley experiment, aiming to observe the effects of rotation and potentially prove the existence of the ether, a hypothetical medium for the progression of light waves. However, the results of the Sagnac experiment and subsequent similar experiments yielded a surprising conclusion. They showed that a stationary object on Earth's surface completes one rotation relative to the fixed stars for each rotation of the Earth. This finding seemed to support the notion of absolute rotation, contradicting Einstein's theory of special relativity, which had discarded the concept of stationary ether. These experimental results reignited the debate over the nature of rotation. While relativity had successfully explained many phenomena related to relative motion, the Sagnac effect seemed to suggest that rotation might be an exception, possessing an absolute quality independent of any reference frame. This apparent contradiction between the Sagnac effect and special relativity sparked further research and theoretical development. It led to the realization that while special relativity does indeed eliminate the concept of absolute velocity, it does not entirely rule out the possibility of absolute rotation. The debate over absolute rotation deepened with the advent of general relativity. Ernst Mach's principle, a hypothesis often attributed to him by Einstein, proposed a connection between local motion and a large-scale distribution of matter in the universe. Mach's principle suggests that the motion of distant stars influences the local inertial frame, the frame of reference in which an object experiences no acceleration. In other words, the rotation of the stars around us could be the reason we feel centrifugal force when we ourselves are rotating. Einstein illustrated this idea with the example of a rotating elastic sphere. Just like a spinning planet bulges at its equator, a rotating sphere deforms into a flattened shape due to centrifugal force. In classic mechanics, this deformation would require external forces acting on the sphere in a non-rotating frame of reference. These external forces could be interpreted as evidence of absolute rotation. However, general relativity offers a different explanation. In this framework, the deformation of the sphere is not due to external forces, but to the curvature of spacetime caused by the sphere's rotation. This curvature, in turn, is influenced by the distribution of matter in the universe as suggested by Mach's principle. While there's no need to invoke absolute space to explain the sphere's rotation in general relativity, the influence of distant stars through their gravitational effects on spacetime creates the appearance of absolute rotation relative to the stars. The local geodesics, the paths that objects follow in curved spacetime, are shaped by the distribution of matter and energy, including the distant stars. This interpretation of Mach's principle in the context of general relativity offers a nuanced perspective on the concept of absolute rotation. This suggests that while rotation may not be absolute in an empty universe, the presence of matter and energy throughout the universe creates a framework within which rotation can be measured and defined, even in the absence of a fixed reference point like absolute space. We've spun through the complexities of absolute rotation, tracing its evolution from Newton's bucket experiment to the nuances of Mach's principle and the implications of general relativity. We've explored the experimental evidence that supports the existence of absolute rotation, as well as the theoretical arguments that challenge it. This journey has revealed that the concept of rotation is not as simple as it may initially seem. It's a concept intertwined with our understanding of space, time, and the fundamental forces that govern the universe. Whether you believe in the existence of absolute rotation or embrace a purely relativistic perspective, the study of rotation continues to be a fascinating and thought-provoking endeavor. It challenges us to question our assumptions about the nature of motion and the very fabric of reality. The quest to understand absolute rotation is far from over. New experiments and theories may yet emerge, shedding further light on this enigmatic phenomenon. As we continue to explore the universe and delve deeper into the mysteries of physics, our understanding of rotation will undoubtedly continue to evolve. If you're intrigued by the concept of absolute rotation and its implications, I encourage you to explore the works of Newton, Mach, Einstein, and other physicists and philosophers who have grappled with this question. Engage with scientific literature and consider the different perspectives that have been proposed. Remember, the pursuit of knowledge is an ongoing process, and even the most fundamental concepts can be subject to revision and refinement. By questioning our assumptions and embracing new ideas, we can expand our understanding of the universe and our place within it. Thank you everyone for watching. My name's the Big Y. Don't forget to drop a like, and if you're new to the Why Not family, a follow. And I'll catch you guys in the next video.